Okay, in this video we're going to cover fluids in motion and Bernoulli's principle. If the flow of a fluid is smooth, we call that streamlined or a laminar flow. This is what we're going to deal with when we talk about fluids in motion. The mass flow rate is the mass that passes a given point per unit time. The flow rates of a fluid must be equal as long as no fluid is added or taken away. This gives us an equation of continuity. In other words, the density at position 1 times the cross-sectional area times the speed at position 1 must be equal to the density times the cross-sectional area times the speed at position 2. If the density of the fluid doesn't change, it can be simplified to the area times the speed at position 1 must be equal to the area times the speed at position 2. Density does not typically change in liquids. This means that where a pipe is wider, the flow is going to be slower. You can see this happening in a river when the water flow is slow when it is wide and fast when it is narrow. Water flows at a constant speed though one section of a pipe. When it enters another section that is half the cross-sectional area, what happens to the speed of the water? Is it A, the speed reduced to 1/4 the original, B, reduced to 1/2 the original, C, stays the same, D, the speed doubles, E, the speed is quadrupled? Hopefully you chose answer D, that the speed is doubled. Water flows through a pipe of cross-sectional area 10 centimeters squared at a rate of 15 meters per second. The cross-sectional area of the pipe is decreased to 5 centimeters squared. What is the water rate in the narrow section of the pipe? Go ahead and pause the video now, remembering to write out your work. Okay, so let's see if you have the correct answer. We're going to use the continuity equation and solve for the speed at the narrow section, which is V2. Substituting in our numbers, we end up with 30 meters per second. Water flows through two pipes that are connected into one larger pipe. The speed in the two pipes is 10 meters per second, and they each have a radius of 5 centimeters. The larger pipe has a radius of 15 centimeters. What is the speed of the water in the larger pipe? Go ahead and pause the video now. Okay, so let's take a look at your solution. We know that the continuity equation is that A1V1 equals A2V2, but here at the beginning we have two cross-sectional areas times the speed. That must be equal to the cross-sectional area of the second pipe times the speed of the second pipe. If we go ahead and simplify, we end up having 2 pi r1 squared v1 equals pi r squared r2 squared v2, solving for the speed in the second pipe and substituting in our numbers, we end up with a speed of 2.22 meters per second. If you didn't get this answer, but you have this formula and it's all written correctly, make sure that you actually squared the radius. A fluid can also change height. If we look at the work done, so here the pressure plus 1/2 rho v squared plus rho gh must equal a constant. One thing this tells us is that as the speed of the water flow goes up, the pressure goes down. You can see that here in the diagram. Here we have the original flow. It goes from a larger tube to a smaller tube, and here you see a pressure difference. A pipe has 3 sections with 3 different cross-sectional areas. Where is the pressure the smallest? Is it at position 1, position 2, position 3? The pressure is the same at all 3 sections. The pressure cannot be determined. Go ahead and pause the video if you need to. Hopefully you chose B at pressure 2. Water flows through a horizontal pipe at a speed of 10 meters per second and a pressure of 2.5 times 10 to the 5 pascals. The pipe narrows and the water speed goes up to 20 meters per second. What is the pressure in the narrow section of the pipe? Go ahead and pause the video now. Okay, so let's take a look at the solution. We're going to use the equation for looking at a height variation. So here we have P1 at position 1 plus 1/2 rho V1 squared plus rho GH1. Okay, and then we set that equal to the same exact thing on the other side. And this is because no energy is entering or leaving the system. So what we start with must be what we end with. Okay, we know that the height difference is going to be 0. In other words, where we start and where we end height-wise is the same. So that means that these two terms are going to cancel out. Now what we have is P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. We're going to go ahead and solve for P2 by subtracting 1/2 rho V2 squared from both sides. We can then factor out a 1/2 rho. Substituting in our numbers here, we end up with a pressure of 1 times 10 to the 5 pascals. Water flows through a horizontal pipe of area 2 meters squared at a speed of 10 meters per second and a pressure of 4.5 times 10 to the 5 pascals. The pipe narrows to 1 meter squared and goes to a height of 20 meters. What is the pressure in the narrow section of the tube? Go ahead and pause the video now. Okay, so let's take a look at the solution. We're going to use the continuity equation at first. We know that A1V1 equals A2V2, so we can find out the speed at the second part of the tube, and that's going to be 20 meters per second. Using our equation, which relates the pressure, we end up with P1 is equal to 1/2 rho V1 squared plus rho GH1, and we set it equal to everything at point 2. The initial height is 0, so this term here is going to cancel out. Okay, and solving for P2, we end up with P1 plus 1/2 rho times the difference in the squares minus rho GH2 is equal to P2. Substituting in our numbers, we end up with a pressure of 1.04 times 10 to the 5 pascals. Now here we had to solve for the speed at the second part because we needed that right here. In the next video, we'll talk about Torricelli's theorem.